Welcome to today's deep dive. We spend a lot of time here talking about the magic of generative AI.
We really do.
And you look at the output, right? The poetry, the code, the essays.
The incredibly convincing essays.
Exactly. And it is so easy to fall into that trap of anthropomorphizing these models. We assume that because they can write like a history professor, well, they must actually know history like a professor.
Which is, it's probably the most common misconception in the entire field right now.
Yeah.
We constantly conflate fluency with factual grounding. We see a model construct this perfect, grammatically flawless sentence, and we just assume there is a structured, reliable database of facts sitting underneath it.
Right. But there isn't.
No, there really isn't.
And that illusion breaks down the absolute second you ask the model to do something that requires rigid precision.
Oh, absolutely.
Like if you ask a standard large language model to just multiply two 4-digit numbers or tell you specifically what day of the week it was on a random date 3 years ago.
It falls flat on its face.
Yeah.
It hallucinates. And it does that because it is trying to predict the answer based on statistical likelihood, not actual calculation.
Right.
It's trying to write the next word in a fictional story about math, rather than actually sitting down and doing the math.
And that is the core conflict we are digging into today. We're unpacking a foundational text in the history of AI. It's a paper from Meta AI Research, led by Timo Schick and his team.
Right.
And it's titled Toolformer. Language models can teach themselves to use tools.
It's a great paper.
It is, and I want to set the stage for you listening right now. Our mission today isn't just to talk about making a chatbot that knows how to open a calculator app.
No, it's much bigger than that.
It is about solving that fundamental paradox we just mentioned. These models are brilliant at language, but they're terrible at facts, terrible at logic, unaware of the progression of time, and they really struggle with low-resource languages.
Exactly. And the industry's response to this paradox has generally just been scale.
Just make it bigger.
Right. If the model is bad at math, throw more parameters at it, train it on more data. But the Toolformer paper argues that, well, that's just horribly inefficient.
Yeah.
You don't need a massive brain to do long division. You just need a calculator.
Which sounds like such a simple aha moment. Just give the AI access to external tools.
Right.
But the execution is where this deep dive gets really fascinating because we aren't talking about hard coding rules here.
No.
This is not some programmer sitting down and writing, if the user asks a math question, then open the calculator API.
And that is the critical distinction we need to make. Hard-coded systems, which we used to call symbolic AI, they just don't scale.
You can't write an if-then rule for every possible weird thing a user might ask.
Exactly. The massive breakthrough in Toolformer is that the model teaches itself when to use a tool, which tool to use, and what arguments to pass to it.
And it does all of this through self-supervised learning.
Entirely self-supervised, no human hand-holding required.
Okay, so let's unpack that mechanism. Because for a lot of people, that sounds like science fiction. How does a probabilistic model, which, as you said, is essentially just guessing the next word, how does it learn to interface with a software API?
To understand that, you have to look at how they structured the training data. They didn't rewrite the core architecture of the model at all.
Really?
No. They simply treated an API call as just another form of language. So, to the model, the text string calculator open bracket 1 + 1 close bracket is just a sequence of tokens.
It's just a word in a sentence.
Effectively, yes.
So it is essentially learning a new vocabulary. Instead of just learning English or Python, it's learning API speak.
Precisely. And the researchers developed this really elegant 3-stage process to teach it this vocabulary. It goes sampling, execution, and filtering.
Okay, let's walk through those one by one. Stage 1 is sampling. What happens there?
So they start with a massive standard data set of plain text. And they show the model just a tiny handful of human-written examples, just that demonstrate what a tool usage might look like.
Okay.
For example, a sentence like, the capital of France is QA. What is the capital of France? Paris.
So they basically give it a few templates.
Yeah, just enough to show the syntax. Then they let the model run loose on the rest of the text data set.
Just reading normal text.
Right. The model reads the text, and based on those few templates, it starts predicting or sampling places where an API call might be relevant. It literally injects these potential API calls into the text.
But at this stage, the model is essentially just guessing, right? It has no idea if the tool is actually going to be useful.
Oh, it has absolutely no idea. It might try to use the calculator to figure out a historical date, or it might try to use the translation tool on someone's name.
Wow.
It generates a massive, massive amount of potential API calls. And frankly, most of them are complete garbage.
Which naturally leads us to stage 2, execution.
Right. This step is purely mechanical. The system takes all those millions of potential API calls the model just guessed at, and it actually runs them.
In the real world.
Yes. So if the model guessed, calculator open bracket 400 divided by 1400, the system executes that math and gets the result 0.29.
Or if it tried to do a Wikipedia search for the Brown Act.
It queries the search API and brings back a snippet of text explaining California open meeting laws.
Okay, so now we have the original text, we have the API called the model guessed, and we have the actual real-world result from the tool.
Right.
But just having a result doesn't mean it is a good or useful result.
And that brings us to the most critical part of the entire paper. Stage 3, filtering. This is the brain of the operation.
This is where it learns.
Exactly. The model has to determine, mathematically, if using that tool actually helped it understand the text better.
This is where I want to get specific about the metrics for you listening. Because when you say helped, how is machine measuring that? It isn't a human developer sitting there giving it a thumbs up or thumbs down.
No, not at all. It relies entirely on what we call the loss function.
Right. Loss.
In training language models, loss is simply a measure of prediction error. It quantifies how surprised the model is by the actual next word in a sequence.
So if the model is confident and gets it right, the loss is low.
Yes. And if it's unsure or totally wrong, the loss is high. And the goal of any model is always to minimize loss.
Okay, so how does it use loss to filter the tool usage?
It sets up an A/B test. Scenario A, it tries to predict the next tokens in the sentence without the tool's help. Scenario B, it tries to predict the exact same tokens, but this time the tool's output is pasted right into its context window.
Okay, I see. Let's use an example from the source text. Say the sentence it's reading is, "The New England Journal of Medicine is published by the Massachusetts Medical Society."
Perfect. So without the tool, when it gets to publish by, the model might guess Harvard or Oxford.
Because it doesn't actually know.
Right. The loss is very high there because it's just blindly guessing. But in scenario B, it uses the question answering tool. The tool returns Massachusetts Medical Society.
And suddenly predicting those exact next words becomes trivial.
Exactly. The loss drops dramatically.
And if the loss drops by a significant enough margin, the model realizes, hey, this tool was useful.
Yes, it keeps that specific API call. It labels it as good data. But, and this is the genius part, if the tool returns something totally irrelevant, or if the model already knew the answer anyway, the loss won't change much.
And in that case, the model just discards the API call. It filters it out. So it's effectively a survival of the fittest scenario for tool usage.
That is a brilliant way to frame it.
Only the API calls that provide a genuine, measurable information advantage survive the filter.
Exactly. And this entirely solves the noise problem. Because you do not want an AI that stops to look up every single word on Wikipedia.
That would be incredibly slow and expensive.
You only want it to look up things it definitively doesn't know.
The paper actually includes a really specific, funny example of this filtering process working in reverse, where the model actively decided not to use a tool.
Oh, the Disneyland example, yeah.
Yes, tell us about that one.
It's a great illustration of the model discerning context. So the training text was describing a quote-unquote Disneyland fiasco with a fire drill. And the narrative continued with something like, "It's safe to say Chewie won't let anyone die."
Okay, and during the sampling phase, the model initially tried to use the calendar tool here.
Right. It saw the word fiasco, it saw an event, and it thought, oh, maybe I need a date for this. So it called the calendar and got back June 25, 2011.
But the date is completely irrelevant to the story being told.
Completely. Knowing that it was June 25th didn't help the model predict the phrase, "won't let anyone die," any better than it could without the date.
The loss didn't drop.
The loss didn't drop at all. So the model learned that in this specific type of narrative context, injecting the date is just noise. It filtered the call out entirely.
That distinction right there between factual accuracy and contextual utility is just incredibly sophisticated. It's the difference between a simple trivia bot and an actual reasoning engine.
It really is. And so after running this process across millions of documents, it creates a pristine data set of truly useful tool interactions. The model then fine-tunes itself on this beta set.
So the final version of Toolformer has learned not just how to call the API, but when it is strategically advantageous to do so.
Exactly.
Let's look at the actual toolkit they provided for this experiment, because they kept it pretty lean.
They did. Just 5 tools. First, a question-answering system based on the Atlas model for retrieving simple factoids.
Second, a calculator for basic arithmetic.
Which directly addresses the precise math weakness we talked about at the start.
Right. Third, a Wikipedia search engine. And the paper notes this uses a BM25 retriever, allowing for broader information lookups.
Fourth was a machine translation system called NLLB.
Which translates up to 200 languages into English.
And finally, a calendar.
The calendar is so interesting to me because it seems almost too basic, but without it, these models are essentially frozen in time, right?
Yes, most language models are completely static. If you ask a standard model, who is the prime minister? It answers based on its training data from whenever it was built, maybe 2 years ago.
Right.
By giving Toolformer a simple calendar, you give it temporal grounding. It knows what today is relative to its own training data.
Okay, so we have the self-taught methodology, sampling, execution, filtering based on loss, and we have our 5-tool toolkit.
Yes.
Now we need to talk about the performance results, because the paper pits Toolformer directly against the giant in the room, GPT-3.
And this is where the efficiency argument really hits home. So Toolformer is based on the GPT-J architecture.
Which has 6.7 billion parameters.
Right. So for context for the listeners, 6.7 billion parameters is essentially a laptop class model. It's
very small. Compared to GPT-3, which has 175 billion parameters.
GPT-3 is roughly 25 times larger.
So just looking at the raw specs, logically, GPT-3 should crush Toolformer on absolutely everything. It has 25 times the brain capacity.
But it doesn't.
Let's hear the numbers.
On the Lemma benchmark, which tests explicit factual knowledge, specifically, the T-Rex subset Toolformer scored 53.5.
Okay. And GPT-3?
GPT-3 scored 39.8.
Wait, the tiny laptop model beat the massive supercomputer model by almost 14 points on a factual test.
Yes, because GPT-3 has to rely on pure memorization. It has to store all those facts directly in its weights. Toolformer didn't bother memorizing, it just looked them up.
It's the difference between memorizing the entire encyclopedia and just knowing how to use a library.
That is exactly it.
And I assume the math results were a similar story.
Even more drastic, actually. On the Emma WPS benchmark, which is for math word problems, Toolformer scored 44.0. GPT-3 scored 19.8.
It literally more than doubled the performance of a model 25 times its size.
Because it offloaded the computation. It didn't try to simulate math probabilistically. It just used a calculator to perform actual math.
And the paper emphasizes how important it is that these are zero-shot tasks, right?
Yes, crucially important. Zero-shot means the model solves these specific benchmark tasks without being shown specific examples of how to use tools for those exact tests.
It generalized the abstract concept of tool use.
Exactly. This proves that a small, efficient model armed with tools can easily outperform a massive monolithic model that tries to know everything.
Which feels like a massive paradigm shift for AI development. Instead of spending tens of millions of dollars training these giant black boxes, we could be building smaller, sharper models that just know how to use existing software.
It points strongly toward a modular, specialized future. But, to be fair to the research, we do have to be realistic about the limitations here.
Right. Toolformer is ultimately a proof of concept, and it has some significant constraints. Let's run through those. What can it not do?
The biggest limitation right now is what they call chaining. The model treats every single tool usage as an isolated, independent event.
Meaning it cannot use the output of one tool as the input for another.
Correct. It can't say, hey, search Wikipedia for the release date of this movie, and then take that date and plug it into the calculator to add 50 years.
It can't daisy chain operations together.
No. It also can't interact with the tools dynamically. It's a strictly one-shot system.
What does that mean for an end user?
Well, think about how you use a search engine. You type a query, you scan the first page of results, you realize your query was a bit vague, and so you refine your search.
Right, you iterate.
Toolformer can't iterate. It generates exactly one query. If the search engine API returns garbage results based on that one query, the model is stuck. It has to proceed with bad information.
That is a bit of a fragility. If the tool fails, the model fails.
Exactly. It lacks that human iterative reasoning loop. There is also a really fascinating finding in the paper regarding scaling laws that we should mention.
Right, because the self-teaching technique doesn't just work on any size model.
No, it doesn't.
But I thought the whole point was that it worked on small models.
It works on efficient models, but there is definitely a floor to it. The researchers tested this exact same training process on very small models, around 124 million parameters, and the technique completely failed.
Why?
The models were simply too small to grasp the abstract concept of tool usage.
So there's a minimum threshold of intelligence required to even realize you need help in the first place.
Yes. The paper suggests this ability to self-teach tool use only really emerges around the 775 million parameter mark. Below that, the model is essentially like a toddler playing with a scientific calculator.
It can push the buttons, but it doesn't understand what the output means.
Exactly.
Another limitation the paper mentioned was sample efficiency, because the training process you described earlier sounds incredibly intense.
It is extremely computationally heavy up front. To find just a few thousand of those useful examples of tool usage, the model had to churn through millions and millions of documents during that sampling phase.
Just blind trial and error to find the signal in the noise.
Yes. So the training itself is quite expensive computationally, even if the final resulting model is cheap and small.
But in the life cycle of AI, inference, which is running the model for actual users, is where the real ongoing cost is, right?
Right. So front-loading that massive cost during training to get a leaner, cheaper model at runtime is usually a very good trade-off for companies.
I want to zoom out to the broader implication here. We are talking about an AI model that actively grounds itself in reality. For you listening to this, why does that matter beyond just getting math questions right on a test?
It matters because it directly addresses the massive trust deficit in AI right now. When a standard large language model answers a complex question, you never truly know if it's hallucinating or not.
Right.
But with Toolformer, if it gives you a precise number, you know it came from the calculator tool. If it gives you a historical fact, you can literally see the Wikipedia API call it used to get it.
It provides its own citations, effectively.
Exactly. It moves us away from purely generative AI, which just creates plausible-sounding text, and toward grounded AI, which anchors its text in verifiable external sources.
It also seems to elegantly solve the freshness problem we talked about. You don't need to spend millions retraining the model every week just so it knows the current news. You just give it access to a search API.
Yes. The knowledge isn't locked inside the model's parameters anymore. The knowledge remains out in the world, and the model simply learns how to retrieve it when needed.
There is one final aspect of this paper that I found profoundly provocative, and I want to leave our listeners with this thought to mull over.
Okay.
We talked heavily about the loss function earlier. The model learned to use these tools not because it wanted to be genuinely helpful to a human, and certainly not because it actually understood what a calculator fundamentally is.
Right. It learned to use them solely because doing so made its next token prediction mathematically more accurate.
It minimized the error. It simply optimized a metric. It figured out that acting like a diligent researcher was just the most efficient way to get a high score.
It's a purely utilitarian behavior.
So here's the question. If a machine can teach itself to use external tools, calculators, search engines, calendars, entirely on its own, just by observing what minimizes that loss function, what other human behaviors might an AI teach itself next, purely to minimize a loss function?
And that right there is the central question in AI alignment today.
Because if deceiving a user somehow minimizes loss, does it learn to deceive?
Yes.
If manipulating a human minimizes loss, does it learn to manipulate?
We are giving these models the agency to choose their own methods to solve a problem. The Toolformer paper proves that they are clever enough to discover tools and strategies we didn't explicitly program them to use, as long as the math works out in their favor.
It proves that how the model solves a problem is becoming just as critical to watch as what the solution actually is.
Absolutely. And it serves as a stark reminder that we need to be very, very careful about what exactly we ask these models to optimize for.
Because they will find the most efficient path.
Even if that path completely surprises us.
They will find the most efficient path. I think that is the perfect summary of both the incredible promise and the underlying risk here.
I agree completely.
Well, this has been a truly fascinating look into the mechanics of Toolformer. It's a bit technical, but it really peels back the curtain on exactly where generative AI is heading next.
It is undeniably a foundational text for the next generation of these models.
Thank you for guiding us through the details. And to you listening, thanks for diving deep with us today. Keep learning, keep questioning, and maybe keep a physical calculator handy just to be safe.
Goodbye, everyone.
See you next time.